Sorry about that, guys. I was told that you guys couldn't hear me. Well, it's just about time to get started. If you're joining me live here, welcome, and thanks for being with me here today. If you're watching this as a recording in the future, I hope you find everything that you're looking for here in this webinar. My name is Simon Kitnick. I'm an applications engineer here with Applied Flow Technology. That means I primarily work with the support team, so I might be a familiar face or a familiar name for those of you who have reached out to the support team for modeling advice or have questions about the software. Today, we're going to do a little studying up at the AFT Library, and we're going to learn all about the Library Manager feature and how to effectively use it in the software. So to give a brief overview of the Library Manager is used to create and save custom data within the software. Today, I'm primarily going to be showing you this in Fathom and a bit of Arrow, but the Library Manager is applicable to all of the AFT products. This means it's included in Fathom, Arrow, Impulse, and Extreme. The Library Manager is going to be a useful tool because it is a way to save that custom data into model files that we may not have pre-built databases or pre-built information for within the software. All of the AFT software is designed as a general tool that's used in a lot of different industries, and modeling really isn't a one-size-fits-all. There's a lot of unique piping systems out there and unique piping components that may require specific data or unique data that we just don't currently have in the software. With the Library Manager, this allows the flexibility for all users to create and input their own custom data in order to properly model all of their systems. Our class schedule here today, or our agenda, since we're going to be doing studying like we're at school, is we're going to first talk about the AFT Library browser. This is essentially the main landing page of the Library Manager. Then we're going to talk about saving and creating custom junctions in the software. We'll talk about creating and defining custom fluids and how all those inputs are used in the software. We'll talk about creating custom pipe materials, then custom insulation layers, custom fittings and losses that are applied within the pipe property windows. And for our SSL settling slurry users, we will do a little bit of talking about solids libraries in the settling slurry module in Fathom and Impulse. So with all that, let's get right into it. Here I've got my application of Fathom open, and to show you where the Library Manager is located, up at the top left here in the menu, there is a library dropdown where you can select from quick access to all of the different categories or jump right into the Library Manager. Once you do that, this will open the library browser. On the left side of the Library Manager here are all the quick access to the different items and categories that we'll be defining today. And on the right is going to be all of the information that you'll be defining and where all of the settings and options you have are for each category. To give a brief overview of the library browser, all of the main libraries that are in the software are going to be displayed here on the left window. The important libraries to note, I'm going to quickly collapse these for better visuals, are going to be the AFT internal library here. This is going to house all of the existing AFT databases, as well as all of these pipe material libraries that are included separate. All of the libraries that are highlighted with this blue highlight are going to be internal libraries for the AFT software, and other libraries that are not highlighted are going to be your own custom libraries. The local user library is stored local to your device and your user on your PC. This is going to be the default location where any new items you create are going to be stored, but these can be moved to external databases and external libraries to be shared more easily. At the bottom here, we have a few different options. We can change the user defaults using the user default button and set as default button. This will change which libraries are loaded upon startup of the software. So if I didn't want to include all of these different steel libraries here, maybe there's something I don't frequently use, I can uncheck those and select Set as Default. Now when I open up a new model file, these libraries are not going to be automatically shown and included in my instance of the software. I can also manually load these defaults by clicking User Default. My current user defaults are going to be just what the standard installation already comes with, so it just rechecked all of these steels that I had just unchecked. To create a new external library, you're going to come down here to the Create a New Library button. When you click this, this is going to open your Windows file browser where you can give the file a name. We're going to call this webinar. And then you can give it a description, which is going to be the name shown on the library browser here. We're going to call this webinar as well. And this will have created an external library that you can use and store all of your information in. As you can see, webinar has populated up here where I can add my custom data once we've created it. The file that we created in our Windows File Explorer is the file you would want to share with any colleagues or coworkers. If you need multiple people to be able to access this file, you would give them that file and they would select Add to Existing Library. They would locate that file that you sent them, and then they would import that into the software and be able to use all of the same custom junctions, custom fluids, any other custom data that you've imported into the software. One more thing to show here in the Library Manager is that you can move data around in different manners. I'm going to just show you briefly with this hot water system library here. This is from one of our example files, but this hot water system contains a few custom junctions. If I wanted to move these junctions from this hot water system library into my webinar library, what I can do is right click on that option here and select Move or Copy Content. Move Content will completely move the content from one library to another, where Copy Content will copy it into another library. So I'm going to select Copy Content, and I'm going to select my webinar library here, and we'll hit select. It'll reload, and now what you can see is that my webinar library contains these junctions that were in the hot water system library. To remove these, similarly, you can right click and select delete content. We're going to do this to make sure our webinar library starts out blank. And now, as you can see, number of junctions equals 0 since we've removed those from the library. So now that you're a bit more familiar with that, we're going to transition to talking about starting to create some of our content. First, we're going to talk about junctions. In the Edit Junctions section, this is going to change the panel that you see here, and at first it's going to be blank. This is because we haven't saved any junctions yet. And you can see our drop-downs for our libraries are going to be shown here, but since we don't have any junctions in our library, it's not going to show anything. So what I'm going to do here is go onto the workspace and quickly create a pump. And I've created a pump curve with some data that I'm going to import here. And so now we've got our pump performance curves here with efficiency and our MPSH, and we're ready to use that in our model. Now, say I wanted to create a pumping station, maybe have multiple pumps in parallel. What I can do to create this same pump here multiple times is I can highlight it and select the library drop down here, and you'll notice there's a new row, Add Junction to Library. We'll click on this, and this will open up a new window where we'll be able to save this pump and this configuration into our library. So what I'm going to do first is switch this to our webinar library rather than our local user. We'll give it a quick name. We'll call this example pump, and then we'll click OK. Now there's two things you'll notice that have changed. First, when we open up this pump, you'll notice that under library junction here at the top of the pump properties window, it's going to show us that example pump is being used. If we create a brand new pump here, what we can do is use this drop down to select example pump again in this new pump, and it will automatically fill out that data. And as you can see, all of our curves were automatically imported into this pump. So this is an easy way that you can quickly duplicate junctions, save configurations, and reuse them in different models. Now, if we look back at our library here, I'm going to click on Edit Junctions to open that up, and we'll switch this to our webinar library. As you can see, we have our example pump saved here. If we wanted to edit this, we can actually double click or select Edit Data to open up the pump properties for this example pump. And if I changed any data here and saved that data, it would actually update all of those two pumps that I drew on the workspace. So this is an easy way that if we did need to make a big change to a lot of junctions that are already saved in our library, we can change it once here, and this will automatically update the existing junctions in the workspace. So that's how you can quickly save and reuse junctions in the AFT software. We're going to press forward and we're going to start talking about creating custom fluids. First, I'll actually show you on the analysis setup. When we're defining our fluid properties, we have this option for a user specified fluid. This is only available in Fathom and Impulse, as more information is required for a fluid in Aero and Extreme. And so we're going to focus on incompressible fluids first before we start talking about compressible fluids. So this will be applicable for Fathom and Impulse exclusively right now. The user specified fluid option gives you the bare minimum requirements that you need to specify a fluid in the software, with density and viscosity as the two parameters you need. Impulse also requires a bulk modulus, and vapor pressure is an optional input from this window. These are going to be fixed inputs, and in Fathom in particular, since a user specified fluid doesn't contain heat transfer data, we're not actually going to be able to model this with heat transfer. As a reminder, Impulse does not model heat transfer at this time. But for Fathom, if we did want to include more data in order to model heat transfer, or in Impulse we just needed to capture a broader range of data, what we're going to need to do is create a user library fluid. Up here, we can select the user library fluid option, and right now the screen's going to look blank because we don't have any fluids included yet. The Edit Fluid List button down here is a quick link to bring us straight into our Library Manager to edit our fluids. So now we'll take a look at this page in the Library Manager. From here, you'll be able to look at all the AFT standard fluids and look at the different curves for their parameters here, if available. The AFT standard fluids, as a reminder, are functions of temperature only. If you want to turn off the AFT standard fluids from this window, make it easier to find your own fluids, you can uncheck this box here that says show fluids provided by AFT Fathom. Again, since we haven't yet created any fluids, this is going to look pretty blank. But let's get right into it and make a fluid here now. When you click on Add New Fluid, a new window will open up where you can enter in all of the data for your fluid. The independent variable, similar to the AFT standard fluids, is going to be temperature by default, but you can also model fluids in terms of solid concentration. If you're modeling in terms of solid concentration, you will not be able to model heat transfer in Fathom. So we're going to stick with temperature here. The minimum required inputs to define a custom fluid here in the library are going to be temperature, density, viscosity, and our maximum and minimum allowable temperatures. The max and minimum temperatures are just limits for warnings and the analysis setup to make sure that you can't define this fluid outside of a selected range. This could be a freezing point or maybe a boiling point of a fluid to limit your range of temperatures to say that we don't want to be able to define a fluid at that low of temperature or that high of temperature. Impulse is also going to require a column for bulk modulus, as this is related to calculating wave speed and communication time. There are further optional inputs here, highlighted in green. Vapor pressure at the very end here is going to be used for cavitation checking, and the other inputs are going to be required for heat transfer, so that's specific heat, thermal conductivity, and on this other tab here for enthalpy data, we'll have reference temperatures and reference enthalpies that will be needed if we want to model heat transfer. So now that I've given you a brief overview of this page here, we're going to create our own fluid, and I'm going to call this grade 22 oil. This was a quick estimation I made and found for the Phillips 66 grade 22 oil. This was compiled from a few different sources, primarily data sheets, but this is by no means a perfect representation of this fluid. So what we're going to do first is enter in our maximum and minimum temperatures at 419 degrees Fahrenheit and -2 degrees Fahrenheit. I've saved all my data here into a CSV file that we're going to input here. I'm ignoring the first line there because I know I had titles in my sheet. And now we can create our curves for our different parameters here. Under enthalpy data, we're going to enter a reference temperature of 446 degrees Fahrenheit and a reference enthalpy of 0. I do want to discuss these inputs a little bit here because this is a common point of confusion when creating a fluid. The reference temperature and reference enthalpy inputs serve as a datum for the software to evaluate heat transfer and enthalpy. So a similar example would be when someone tells you they're at 1,000 feet of elevation, you're most likely going to assume that this is 1,000 feet above sea level, where sea level is that reference point or that datum. Otherwise, how would you know exactly where that person is, what their elevation is? Is that 1,000 feet above ground level in Colorado here, where I am? Is that 1,000 feet above ground level in a completely different country? You need a datum point in order to, a datum or a reference point in order to define or fully explain where that person would be at elevation, or in this case, where your enthalpy and temperature are. So different standards use different values for these reference temperatures and reference enthalpy. The normal boiling point is a commonly used one where you assume 0 enthalpy at the boiling point of the fluid. That's what I used here. ASHRAE uses a 0 enthalpy at a temperature of -40 degrees Celsius for saturated liquids, and the International Institute of Refrigeration uses an enthalpy of 200 kilojoules per kilogram at 0 degrees Celsius. So there are a number of different standards that have different definitions for what these references should be, but this is really only important if you're actually using enthalpy data specifically. Otherwise, they're relatively arbitrary and they're only used for that reference. Hopefully that provides a bit of clarity on how to input these parameters, because this is a common point of confusion for what do you actually input here, since this is not going to be typically something you'd be able to get from a manufacturer. With all that being said, and our fluid fully defined, we're going to select OK, and now it appears here in our library. We're going to return to the analysis setup here, and I just double click to reload this page, and you'll see that we have our grade 22 oil shown that we can add into the model. Those temperature ranges, that max and min, are going to show up here to warn us that we can't operate between under -22 degrees and above 419 degrees, sorry. And our properties will be automatically calculated here based on those curves we entered when I enter in different temperatures. So that's how you can define custom fluids in Fathom. Let's take a look at Aero and talk about compressible fluids. So it might have been a little subtle there, but I did switch over to Aero. We're going to open up the Edit Fluid section of our library, and this is going to have the same layout as Fathom and Impulse would within compressible fluids, but they'll be different fluids since they're gases. If we click on Add New Fluid here, again, the layout's going to be very similar, but you will notice there are a number of different requirements. For compressible fluids and gases, the minimum requirements are going to be temperature, viscosity, specific heat, maximum and minimum allowable temperatures, and we're going to need a molecular weight here, as well as our reference temperature and reference enthalpy. These still serve as a datum, the reference temperatures and reference enthalpies, but this may be a more relevant or a useful parameter in Aero because compressible fluids do require more heat transfer information, making enthalpy a more useful parameter. If we go back to our raw data here, thermal conductivity is needed for more complex equations of state models. Vapor pressure is going to be used for checking for saturation. And you'll notice we're going to have several columns for enthalpy and density here, where we can specify these enthalpies and densities at different pressures. This can be used to directly find values for this information when the existing equation of state models that we have in the software may not be applicable. We have had customers that have had fluids that don't behave according to any of the fluid models we currently use in the software, but they have custom data here for enthalpy and density. So this is where you can specify that if you are using a very unique fluid. The other constants found in the other data section are all going to be related to different equation of state models, and depending on how much information you're looking to use, which equation of state model you're looking to use, you may need to input different parameters here. So let's start out and create a fluid for natural gas. This was an estimation I created with a fluid property viewer. It's primarily composed of methane, ethane, propane, and some other hydrocarbons. I have my file here that I'm going to import into the software, which is going to include the minimum input for fluid. Our maximum allowable temperature is going to be 200 degrees Fahrenheit, and our minimum will be -20. Our molecular weight is going to be about 14.6. And our reference temperature here is going to be 32 degrees Fahrenheit at 0 enthalpy. So what we've done here is I've specified only the minimum required inputs in order to create a fluid, a compressible fluid in Aero. And I'm going to show you briefly here what it looks like in the analysis setup. Similarly, if you're not familiar with this interface, it's very similar to Fathom, where we're going to select user library fluid, and then we can see our natural gases here. When we add this to the model, you'll notice that the only available equations of state that we can use are the ideal gas model and the constant Z or constant compressibility factor model. Similarly, we're only going to be able to use the reference enthalpy model. Now, I'm not going to dive into exactly everything that these models mean and do. That's a story for another time. But I did want to show you how, with only the minimum input shown, we are limited in the equation of state models and enthalpy models that we can use. So now let's go back and locate our fluid here in the library, and we're going to add more data to that fluid. So I'm going to import a different file here, which contains more data. And I do know that there are a few columns that aren't going to properly get copied. So I'm going to copy those manually here, bear with me. We've got columns for that there. And our density columns as well, down at the end here. So all I did there was I copied these in manually. Now under other data, we're going to add in all of our constants here. Our compressibility factor is going to be 0.985. Our critical pressure is going to be 619. Critical temperature is going to be -157. An eccentric factor of 0.011. And then we're going to enter in the pressure values that will be used for our enthalpy and density curve fits. If I didn't show this directly, When these columns are set for enthalpy and density, they do actually need a specific pressure listed, so you can enter those pressures here. And I want to make a note that all of this information that I just put in and obtained was all through a fluid property viewer, where I was able to specify the content of my fluid, and it would automatically calculate all of these parameters for me at different pressures and at different temperatures. So now that we've defined all of this data, we're going to regenerate our curve fits here, and we'll reload this section here in the analysis setup. When we add this to the model, you'll notice that a lot more equation of state models are available, and a few more enthalpy models are available as well. By having the fluid fully defined with all of these additional constants, this allows us to use more complex equation of state models. The critical pressure and temperature allows for the Redlich-Wong model, while the eccentric factor allows for all of the other models to be used. I do want to note specifically that there are two models here in both enthalpy and equation of state called table. These models are going to relate to the enthalpy and density data I talked about earlier, where we specifically put in enthalpy at different temperatures and different pressures. Same with density. Those are the columns I copied in manually. This data is used only in these models if you want to directly model the enthalpy of the fluid and the density of the fluid. And what this does is it will interpolate between the data sets you entered into the fluid during calculation and during modeling in the software. That means that what you need to make sure you do is that if you are using these methods, make sure that your operating range does fall within the lowest and highest temperatures of enthalpy and density that you provide in the library. So with all of that being said, I do want to acknowledge that there is a lot of data that you need to specify in order to create these fluids that is not always easy to obtain. In fact, most of the time, this data is not going to be obtainable for a lot of fluids unless you're using a specific fluid property calculator or something similar. I want to remind you all that modeling is already an approximation. It's not going to be exactly perfect, and there's always going to be things in real life that aren't perfectly accounted for in software. So when you're defining fluids especially, it's important to know what you're looking for. How precise do you really need to be? How accurate do your results need to be? What margin of error do you have? And do you need to capture every possible data point? Always remember that modeling is a game of trial and error and a game of approximation. We want to make the model as close as possible to a real system as we can, but sometimes data just simply isn't available in order to do that. It's always okay to use approximations, but what's important is to remember the assumptions that you're making when you're using these approximations. If you are using any approximations that may deviate from what the real system is doing, it's important to know ahead of time how that may impact your calculations, what kind of safety factors you may need in order to properly account for that, and use your best engineering judgment to make sure your model is as accurate as it can be with the data you have available. For fluids specifically, there are a lot of fluid property calculators online that can be useful tools to help calculate different values of different parameters here that you need to define in the software, as well as manufacturers can occasionally provide additional data that may not be available in data sheets and specifications online. And you can always use our scenario manager tool to compare different scenarios with different definitions and maybe see how those results deviate. With that all being said, I hope you feel a little more comfortable. I know there's a lot of data defined in fluids, but hopefully that gives you a little bit of a relaxed feeling of how you can actually continue to still use this and continue to define your fluids, maybe without having every possible data point available. With that, we're going to press forward and we're going to go on to our next topic here and talk about pipe materials. Actually, I'm going to switch back to Fathom for this. So if we open up our library manager once again and we go to edit pipe materials, this is the window you should see. First, I want to talk about the tree that we have here of pipe materials. Similarly to the library browser, there's going to be a blue highlight over the read-only or AFT included pipe materials. And now the organization of these pipe materials starts with the material at the very top level. On the center here, we have our different sizes. And at the very bottom, we're going to have our type or our schedule, which is the lowest level here of the pipe. If we take a look at this on the workspace, we're going to see similarly that we have our pipe material here, which was our top level. Our size is going to be shown here. And then our type is going to be shown here, where we can select our different types or schedules, our different sizes, and our different materials. And we're going to go back to the library. I also want to make note of the sections over on the right where there are friction sets, insulation sets, and pipe thermophysical properties. Make sure you guys can see one here. So I just selected the copper pipe so that you guys can see. The friction and insulation data sets are used to quickly select friction data or insulation data for pipes on the workspace. And the thermophysical properties are used for heat transfer, cost calculations, and wave speed in impulse. Different products have different requirements for the pipe thermophysical properties. So depending on which product you're using, if you're creating a pipe material, just be sure to check the specify properties section here and review which is required and what inputs are optional. So let's get going right into it and show you what it looks like to create a new material. To do that, what we're going to do is select pipe materials up here to make sure we're adding to this line of materials here. And then at the bottom, we're going to click new material. I'm going to create a material type for carbon steel. And our first size is going to be 1 inch. Our material type or schedule, we're just going to start with standard. There are a number of different geometries that you can specify here, and as you're using different geometries, you'll see that there are different requirements that are going to populate down here below in order to define that pipe. We're going to start and just do a simple cylindrical pipe. Our inner diameter is going to be 1.049 for our standard schedule. And our wall thickness is going to be 0.133 inches. This is an optional parameter, but it saves a little bit of time in the actual pipe property window when you're doing heat transfer calculations. Otherwise, you'll have to just enter this manually later. Our friction data set description is going to be the name of our friction set. We're just going to call this new to refer to this as a brand new pipe. And our frictional value here going to be 0.008 inches for in the absolute roughness model. If you are using different friction models, we have a number of those available here, which you can select from and enter the appropriate friction value for that. Once we click OK, that's going to create our pipe material here. And as you can see, we have our top level material, our size, and our type or our schedule. When we first created this material, we needed to define all of the parameters shown in that window. We can create new sizes and new types directly here by selecting the 1 inch size and clicking new type. This window will open up again, but as you can see, we actually don't need to define all of the information anymore since the carbon steel, the size is already selected, and similarly, the friction data set has already been created. We're going to start out and make a new type here for our 1 inch size. This is going to be 10S, where our inner diameter is going to be 1.097 and our wall thickness is going to be 0.109 inches. This is a slightly larger flow area and slightly larger wall thickness. And once we've created that, as you can see, we've got our new schedule or type shown here. Similarly, we can create a new size by selecting carbon steel here, by selecting our material, and then clicking new size. Again, we'll need a few different parameter inputs here where we'll also need to enter our size directly, but the rest of the inputs have already been included. This will be a 4-inch size. Our material type or schedule is going to be standard. Our inner diameter is going to be 4.026 and our wall thickness will be 0.237. And we'll click OK here. And as you can see, now we have our new size populated here with another schedule. And same thing as before, if we wanted to make a new schedule here, we can do the same thing where we define our parameters like so. And I did that quickly, but the process is the same. We provide our inputs and we can create that type. We're going to make one more size here. This is going to be our 8-inch size with our standard schedule and our inputs here. And as you can see, now we've created our 3 sizes with a variety of different schedules shown for each one. I'm not going to create another schedule for the 8-inch size. I think you guys probably get the idea. What I will do is create a new friction set for these pipes. I'll make sure to click carbon steel, so when I'm creating this friction set, it is applied to all of these different sizes. And we're going to click new data set here. And we're going to call this one worn. So this is essentially a different friction set that I'm going to use maybe for a pipe that has been in operation for a long time, may have some wear and tear, may have some buildup, something like that. So I'm creating this friction data set here that I can select for pipe that have a much higher roughness. We're going to skip over insulation data sets and circle back to this later when we start to create our custom insulation, but we will specify our pipe thermophysical properties here. I do have a table that I can use for this, but I believe it won't import correctly because I didn't format it, so give me just a second here. And these are actually going to be in metric units. So I'm going to change these values here. I think the modulus is actually in PSI. So similarly to fluids, when we're creating our pipe thermophysical properties, we'll need our temperature, our thermal conductivity for heat transfer, and our modulus of elasticity. This is going to be a required parameter in impulse, again, for wave speed and communication time. We're going to have to enter our maximum allowable and minimum temperatures. I didn't mean to put a negative there. And our density here as well. Density is used if you're doing specifically cost calculations. And if you don't have the material density directly, we do have a converter here where you can do unit weight to density. And just for show, if we enter in our outside diameter, we'll use our 4-inch size, which is going to be 4.5 inches. That's the inner diameter plus 2 times the wall thickness. And our inside diameter is going to be 4.026. Our weight per unit length, and this was what was provided on my data sheet, is going to be 10.8 pound mass per foot. And we can select calculate density. We'll change this into inches. And as you can see here, 0.283, very close to the material density I had found of 0.284. So this is one way you can quickly calculate that density if you're not directly provided the material density, but provided a weight per unit length. You can click OK, and that will automatically populate there. So now we've specified and created our curves for our pipe thermophysical properties. Let's see what that looks like on the workspace. So if we go to the workspace here, we'll have the option to select our pipe material from our list. We can select our different sizes that we created and our different schedules. And down here under the friction model, we'll have the option to select between our two friction models that we created, our new pipe and our worn pipe, and that'll automatically change our roughness value. For heat transfer, I need to turn that on real fast, make sure we're using our fluid here. If we take a look at heat transfer, oh, that didn't save properly because I didn't save the, let's see, bear with me just a moment. Oh, we'll just use this. Maybe that was the reason. Okay, there we go. Now we're properly showing heat transfer. What we can see here is that our pipe wall, we have the option to choose the conductivity from our library since we specified that thermophysical conductivity curve, and the thickness will automatically be pre-filled here because we defined that in our pipe creation. Otherwise, it would simply be using user specified, entering the conductivity directly, and if we didn't specify our thickness, we would have to enter this directly as well. So that's how that's used in heat transfer. From there, let's go forward onto our insulations. This is going to be defined very similarly to pipe materials, where we'll create our insulation name. I found a quick data sheet online for a nitrile insulation, and we'll enter in our data here. I'm going to import in my data for that insulation here. I believe this was degrees Celsius. And that should be watts per meter Kelvin. And similarly, we enter in that data, create our curve of density. Let's see, what was our density? Okay, it was about 100 kilograms per meter cubed. So all of this data is pretty easily locatable on data sheets. This is one of the more simple things to define. So we've created our thermal conductivity curve so we can see the heat transfer through this material. And now we're going to go back to our pipe materials and we'll talk about insulation data sets. An insulation data set is similar to a friction data set where we specify what insulation we want to be using on our pipes. I didn't click save, that's okay. So I didn't actually save our nitrile resolution there, unfortunately, so we're just going to show you with polyurethane, simple thing. We'll do a 1-inch thickness here. And we've created this data set here. Now, if we go back to look at the pipe here, and we look at the heat transfer, what we'll see if we add an insulation layer is that we have the option to use in our material library here, where this is already set by the conductivity curve used in the in this data set we just made, and the thickness is set by that as well. Otherwise, it's as simple as using the insulation library or user specified, using our drop down here to select the different option, and then manually specifying our thickness. The insulation data set can be one way to save a bit of time creating those insulations in the pipes, but it's something relatively easy to define as well. Those different insulation libraries that we would create would be shown up here if I had saved it properly, and then we can select those and manually enter those thicknesses appropriately. So now if we go back to our library here, we're going to move on and talk about fittings and losses. So actually I'll show you first, for those unfamiliar, the fittings and losses section, oh, that's interesting. The fittings and losses section is a section within the pipe where you can specify losses directly within the pipe rather than drawing them as a junction on the workspace. In the fittings and losses window here, you can see that we have a library of a variety of different losses shown. These come from a number of different sources as indicated down here, and these will add a loss coefficient into the pipe based on the different component that you have. It's important to keep in mind that when you do this, this is only going to serve as the actual loss value applied over the length of pipe. That means that if we added a check valve here, it's not actually going to behave as a check valve if there were reverse flow in the system. It's not going to prevent that. It's purely adding in a K-factor loss associated with what was tested as this swing check valve. This one in particular I included here was from Crane. So through Crane's testing, he determined a loss factor associated with a 90-degree seat swing check valve. That is the only part that's going to be applied to the pipe. It's only the loss, not the behavior. So we can create these ourselves similarly in the Edit Fittings and Losses section of the library. If we select Create New Loss Item, you'll see that all of the inputs are shown here. The source is always going to be user-defined since we're creating it. The category is going to be one of the categories shown before, all over here. It does have to fit into one of the existing categories we have, but there is a section for other if there's something that just doesn't fit directly in the categories provided. For this, we're going to just do an elbow/bend. The type can be renamed, and what this is going to do is change the name of this here. So if we did want to create a new subsection under elbow and bend, we can actually rename this to be what we want it to be. Otherwise, you can select from the already existing types. We're going to stick with the standard threaded here. Subtype similarly can be renamed to create new types under that section. And just to expand out a few here, as you can see, all of these are named based on the different parameters that are used for that fitting. Under the standard threaded and miter bends, these are just generals. And then moving on to geometry, we can see that you can also specify that geometry, and this will take its form in the tree of names over here as well. For me, we're going to specify an angle of 70 degrees. And lastly, you can enter your K-factor loss model, either a constant K or the Crane definition of that K-factor loss, and the value associated with that. In the reference or notes section, if this is taken from a textbook or from a different data sheet, you can include that here to reference later. Once we hit accept, you'll see that this created this new 70-degree U to indicate user defined under our general subtype, standard threaded type, and elbow bend category, the same way we defined it over here. Now, if we go back to our pipe and open up that specify fittings and losses section, we'll go to bends, standard threaded, general, and here is our 70-degree user specified bend. And we can add any number of these into our pipe, and it'll create the associated loss factor for that bend. When we click OK, we'll see this show up here, and we'll see the total K factor that's being applied over the length of pipe to add in that additional loss. So even though we didn't actually draw all 4 of those bends directly, the associated K factor, the associated loss due to those bends was captured in that pipe and will be modeled when we fully create a model here. On to our last item of the day, we're going to talk about solids and solid libraries. So this is only shown with the settling slurry module active in Fathom and Impulse. So I'm going to create a new scenario here just to have some differentiation where we're going to activate our SSL module. If you're unfamiliar with the SSL module, please note that I'm not going to go overly in depth into all of the different parameters and explanations of the module. My goal is simply to show you how to create solids within the library for this module, but we do have a lot of other resources on our website that can help with any confusion for anyone who might not be familiar with these parameters or how they're used, or might not be familiar with the settling slurry module itself. So if we open up the library, what we're going to see now that we have the settling slurry module active is that there is this new Edit Solids section. We're going to create a new solid here, and this will open our solid physical properties window. The temperature dependence of the solid isn't always known, and by default, you can assume constant properties with no relation to temperature. But if you do have temperature available for the solids, you can uncheck this Use Constant Properties box and input that data directly. Similarly to our forms before, we have temperature and density as our required inputs, and specific heat and thermal conductivity are required if we're modeling heat transfer. So I'm going to create and start defining our solid library here. This is just going to be a rough estimation for sand. And I've created this file ahead of time to use here if it's going to work. No worries, I can copy this directly. So now I've entered in this data. I am going to use temperature dependence, so I have this box unchecked, and we can create curves for that similarly to what we've done with our pipe materials, with our insulations, and with our fluid properties. Under other solid parameters, there are required inputs here as well, where we're going to need a terminal velocity parameter. For this, I'm going to use a value of 0.55. We're going to leave our stratification ratio as calculated, and we're actually going to use a particle size distribution rather than specifying a direct D50 and D80. Let me grab this really quickly from my document and enter in that data here. Actually, before I do that, I want to note that if you're familiar with the different models in the SSL module that we have, some of them use different mesh types. You can use this dropdown to define a predefined Tyler mesh or granulometric spread distribution rather than a user-specified mesh. If you are creating these solid libraries, just make sure you know which settling slurry model, loss model you're going to be using ahead of time, and whether this requires a mesh and how to define that mesh properly. So we're going to just do a simple user-defined mesh here, where I've entered in my data for particle size and percent retained on the mesh, and that fully specifies our solid. When we click OK here, you'll see it shows up in our library, and if we open the analysis setup window, just add a few parameters here to make sure this is shown, and make sure we're using one of these settling slurry models here. Now, if we go to our solids definition, you'll see that the from library section, we can select the solid library we created, where it will automatically input all of this information. It'll automatically load our mesh here. And depending on which model we use, it'll load that data as needed. So if you are a user of the settling slurry module, this is one way that you can save a little bit of time. If you have data known for your solids, that you can add those into your library and reuse them in different models. This can be helpful if maybe there's a common fluid or common slurry that you're piping from different locations at different facilities. You can save this solid into your library to easily be used later in different models and different configurations. So we've gone through all of the different libraries, engineering libraries that you can do here in the Library Manager. Note that there are cost libraries, but this is a beast of its own that we have a lot of other resources for online and is likely shown in another video. Hopefully you found all of this information really useful, and this will help to create a lot of custom components in the libraries for you. With that, that brings us back to our presentation here, and that brings us back to the end of the webinar. You all survived the school day and the schedule here. Great job. As always, we have a lot of resources available online if you're ever looking for more information or help with the AFT software. We have plenty of resources on our website, as well as we offer consulting options, and you can always reach out to us directly at support@aft.com for direct questions. Thank you all for attending. If you have any other questions, please email us to let us know. I will stick around for another few minutes here to answer any questions you guys might have. Otherwise, I hope you enjoyed the study session here today and learned a lot about creating custom libraries within the AFT software. Best of luck to all of you with your projects and models, and have a good time. Okay, I do see a question that came in here. Can Arrow calculate two-phase steam flow? Unfortunately, Arrow does not have the capability to do two-phase flow just yet. It is something we do want to include in the future, but I don't have a current timeline of when that will be available. Arrow at the current moment can only do single-phase gas compressible flow. I do see another question here. Is there any chance of adding diaphragm valves to the valve list? We have a number of requests to add a variety of different components into the library. I'm not entirely sure if diaphragm valves are part of that list, but I can certainly add it to that list. This is something that in order to add stuff to the AFT library, we need to have a number of resources and loss models that kind of explain the behavior of those valves or of those components through the fluids. And sometimes or through the components, sorry, not through the fluids through the components. But sometimes we just don't have that data readily available yet, or don't have the resources in order to add that into the software. It is something that we want to expand in the future, but as of right now, I do not know if that's something we're actively pursuing. We have another question here. What is the purpose of the ASME steam table in Arrow? The ASME steam table is just another database to provide more accurate and different information on steam specifically. It was a commonly requested database from many years ago in the Arrow software for high pressure, high temperature application steam modeling. The main purpose of it is just to provide you with another resource already built into the software that can model that application. It does have different requirements and different parameters than what the AFT standard steam does. The AFT standard fluids, like I discussed, are only functions of temperature. So the ASME Steam library just has more information available and can model it probably to a higher degree of accuracy than the AFT standard can, but it is going to make your models take a longer runtime. There might be more calculations that it's doing. It's using more parameters. So it's more of a, I would say it's more of a higher accuracy model to be used kind of in final passes of looking at a model, and only applicable for Steam, since that's specifically what that library is designed to handle. All right, everyone, so we're just over time here, so I'm going to stop taking questions. If you have any more questions, definitely email us. You can email me directly at support@aft.com, or you can email us at webinars@aft.com if you have any further questions or anything else you'd like to discuss from this webinar. I hope you all had a good time and best of luck with everything.